Hello friends, it's MoNaCo here, and honestly I can't believe it. We're almost done. Our last unit, nuclear chemistry. We're going to be talking about some of the basics of notation in nuclear chemistry in this lecture. We're going to compare the types of transmutation reactions that can occur. We're also going to look at the types of radioactive decay. We're also going to be able to determine if an element is going to be radioactive or not just by looking at the periodic table and its isotopic mass. So when we started the year, we were talking about protons, neutrons, electrons, how those are all made up into atoms. And we've never really approached the fact that the number of protons and neutrons can change over time and within the nucleus of an atom. So this entire unit of study is about the nucleus of atoms, hence nuclear chemistry. Not necessarily nuclear bombs, but nuclear chemistry, because we're talking about the nuclei of atoms. So the protons and neutrons give the identity and mass of an element. In this unit, we'll look at what happens when the ratio of neutrons to protons leads to an unstable nuclei. What happens then? What happens when you break apart a nucleus? What happens if you force two nuclei together? This is the study of nuclear chemistry, reaction of the nucleus, radioactivity, and transmutations. Everybody knows radioactivity is dangerous, but did you know that you're constantly getting a dose of radioactivity from everything around you? So basically, there's a lot of annotations to do in this unit of notes. So the study of reactions that are caused by a change in the nucleus is nuclear chemistry. That's that small center part of the atom. This causes the element to become something else, to become another element. The word for that is a transmutation. So one element turning into another is called a transmutation. This has nothing to do with electrons, just protons and neutrons, since those are the things in the nucleus. We're ignoring electrons and the electron rules. The stability of nuclei. Basically, I think of the nucleus of an atom like a Jenga tower. The larger, the bigger, the taller the tower it is, the more unstable it's going to be. And nature follows this kind of stipulation. Any atom with atomic number greater than 83 is naturally radioactive. So anything heavier than bismuth, so bismuth on our periodic table is the first naturally radioactive element because it's got an unstable nucleus. The ratio of protons to neutrons is not a 1-to-1. It's kind of like a 3-to-1 type of thing. And this is not safe for the nucleus. They don't have stable isotopes, so they're continually decaying or turning in through transmutation into other elements. Now, small atoms can be radioactive too, even though most of them are stable. They're not usually naturally radioactive if the atomic number is less than 83. There are exceptions, obviously, because the typical mass as reported on the periodic table is the mass for the stable isotopes. So if you're looking at the periodic table for carbon, the square says carbon, 12.011, carbon, and 6. So the typical atomic mass is 12.011. But if we look at these isotopes, carbon-13 and carbon-14, those numbers, those are not the typical mass. So these will be radioactive or unstable and transmute into other elements over time. There's an entire reference table that we're going to get into more depth later on, reference table N, that lists the elements that are unstable, okay, and their radioactive decay mode, so how they turn into something else too. Here is some examples where we're going to be looking at the periodic table's mass and comparing the nuclear symbol given to the periodic table mass to determine if it's stable or unstable. So I've got my periodic table with me, and the first element we're going to look for is calcium. I'm going to write periodic table mass in there. So calcium It's got 40.08 Ca, and of course it's got 20 protons because otherwise it wouldn't be calcium. So we look here, the nuclear symbol 37 is not the same as 40. So this is an atypical isotope of calcium, and we would say that it is unstable because 37 is not equal to 40. Therefore, it's unstable. If we look at the next one, hydrogen 1H1. Well, on our periodic table, it says 1.00794 is the average atomic mass of hydrogen, and all of them have 1 proton. And we look and we compare this number, that atomic mass, with this one, and we see, well, that's pretty much equal. No, it's not identical, but it's darn close enough. So we would say, therefore, this is stable. It's not going to be radioactive. Look for some oxygen on our next example. Oxygen on the periodic table says 15.9994, and we've got 8 protons. And again, we're comparing the atomic masses. 16, 15.999, that might as well be equal. So therefore, we've got ourselves a stable isotope. You must do those 2 examples yourself. I mean, I'm just looking at the periodic table and doing what I told you to do. So what happens to a substance with an unstable nucleus? I mean, so what? It's stable, it's unstable, who cares? It's going to naturally decay to form a more stable substance or an element. We call that naturally decay. The spontaneous is natural transmutation. Now, natural transmutation occurs whenever an unstable nuclei falls apart into something that is stable. And now we get to the actual textbook definition of transmutation. It's the changing of a nucleus of one element into the nucleus of another element by gaining or losing nucleons. Those nucleons are protons or neutrons. It always decays into a more stable element. So we're going to gain or losing protons or neutrons from our nucleus in order to keep these radioactive isotopes stable. It's what nature does. So the 2 types of transmutations are natural, which happens when unstable atoms with atomic number greater than 83 turn into stable ones. And here's our first taste of a nuclear equation. We've got unstable uranium, 238. Look at the periodic table. Uranium is greater than atomic number 83, so it is automatically unstable. According to reference table N, it goes through alpha decay. We'll get into that a little bit later. But when an unstable uranium falls apart, it turns into a helium nuclei, an alpha particle. We'll see what that is later, and something else. The great thing about nuclear chemistry is we always have to conserve mass, just like in any balanced equation. So what you do is you got to say 4 plus something equals 238. So if you think of this as a 234 plus x is 238, and 92, 2 plus x is 92. So what we're doing is we're figuring out the atomic mass and the atomic number to figure out what the new element would be. So 238 minus 4 is 234. That's going to be the mass of this new element. And the identity of this new element is going to be atomic number 90, which I'll have to look on my periodic table to find. And there it is, TH, thorium, for Thor, the god of the Norse god of thunder. Natural transmutation includes the following: alpha beta positron emission, the sun, and electron capture. The sun is what is occurring in, well, our sun. The star of our sun has got some natural radioactive decays going on in it. Now, the artificial transmutation, this is what happens when we got a stable atom. We hit it with some high energy particle to get a chain reaction to start to happen. This happens in nuclear reactors, nuclear bombs, particle accelerators. So very high-tech pieces of scientific machinery can do this. So what we've done is we take a stable nucleus being bombarded. Here's a stable nucleus, nitrogen. That's stable. And we hit it with some helium particles. Now, the same deal works when we're doing our transmutation here. We add the atomic masses, we add the atomic numbers, and we figure out which element we've got. 14 plus 4 is 18. 7 plus 2 is 9. So atomic number 9 with a mass of 18, atomic number 9 is F for fluorine. Now, atomic number 9, fluorine, has 18.99, so this is a radioactive or unstable version of fluorine because the periodic table says the stable mass is for a 19 AMUs. So these types of transmutation, bombarding of any nucleus in a particle accelerator, so particle accelerator. The fusion, combining nuclei of the atoms, this happens in the sun and some research laboratories. Or fission, splitting the nuclei. This is in the reactors, nuclear reactors, and nuclear bombs. This type of thing happens in those. Scary stuff, but really do have some benefits as well. Usually we just hear about the detriments, though. Now, table O in our reference tables goes into the details about what these different radioactive decays are. So these are symbols used in nuclear chemistry. So we've got our alpha particle. There's some notation involved on our periodic table and our reference for these. They can be done a couple different ways. A 4He2, or for the Greek symbol for alpha 2. The mass of this is always going to be 4 AMUs. These aren't dangerous to us. We're actually being hit with these all the time. Your skin will stop them. Skin stops them. And paper also stops them. So this is the most harmless form of radiation. So the most harmless type of radiation. Okay, we're being hit with that all the time. Not a ton of it, but we are being hit with it all the time. Your body, your skin, a piece of paper will stop this stuff. So your clothes will protect you from alpha particle radiation, which is just one of the ways a particle can fall apart, the nucleus. Now, beta particles are notated because they're forms of electrons. It's like atomic nucleus losing an electron. So the way that we draw these are 1 or 0 E negative 1, or 0 beta negative 1. So the beta particle is basically an electron, and somehow magically the nucleus can emit an electron. It does some weird stuff in there with a soup of protons and neutrons and all the stuff that's going on. The mass of these are 0 AMUs. These don't have any mass, which is why they are dangerous. Okay, if they have no mass, it's very difficult to stop them. Beta particles are technically a little bit slow moving. They're dangerous internally and externally, meaning if you swallow a beta particle source of radiation, you could damage your body. Tinfoil or cardboard would stop these, so you need a little bit more protection from them. So this is not the most harmless type of radiation, but the second most harmless. Now, a positron's a really weird thing, and we haven't seen this term until now, but a positron is, well, it's an electron with a positive charge. Say, what? Well, it's something that really, it exists. It's true. A positron emission, a PET scan, uses a radioactive isotope to emit positrons to scan the human body for dangerous diseases and stuff. It's like a CAT scan, but it's a PET scan, it's called. These, again, have no mass, 0 AMU. And since they have no mass and the opposite charge of an electron, this, again, the cardboard or tinfoil is going to stop it. The most dangerous source of radiation, and this is the type of radiation that kills. Okay, this is the type of radiation that you got to protect yourself from with like lead vests and jackets and really heavy-duty gear. Nuclear reactions in reactors and bombs produce this stuff, which is why it's so dangerous. A gamma ray is something special. It's got no mass, and it's got no charge. It's a piece of energy that just goes. It doesn't stop very well. So this is the most dangerous radiation. Now you might say, well, these particles have no mass or charge. How could a nuclear isotope change from one element to another by emitting something that has no mass or charge? Well, these are emitted in addition to other particles. Very dangerous, highly penetrating. You need a very heavy lead shield or suit to protect yourself. Nuclear reactors are encased in steel and concrete to protect the operators and the communities from them because they all produce gamma rays radiation. Radiation can damage our cells and cause mutations to form, which, not like Spider-Man mutations, we're talking like genetic mutations that lead to cancer. These nuclear particles were originally discovered by passing a radiation source through electrically charged plates. The positively charged particles would be attracted to the negative plate, and the negatively charged particles would be attracted to the positively charged plate, and the neutral particles, like the gamma rays, would go straight through. They wouldn't be diverted at all. So this little experiment here proved that these particles that were being emitted by the radiation sources had a charge and a mass. Positive alpha particles attract to the negative plate, right there. Positive alpha particles, that's 4He2. Negative beta particles, 0E, -1, positive plate. Gamma rays, 0, 0, gamma, are no charge, no mass, so they are not deflected at all. So at this point, I want you to have a basic understanding that a nucleus can undergo changes based upon the ratio of protons to neutrons makes it stable or unstable. Artificial and natural transmutation reactions are those ones that we did the little flow chart for. I want you to begin to understand the basic notation of nuclides and their nuclear particles based upon Table O. There's a couple pages in our practice for you to do here and a prep assignment on Castle. So thanks for watching. There's only 3 more lectures after this and we are done with the course. Thanks. Bye.